In this problem, we are given a sequence defined by the recurrence relation, and we'd like to find the limit as n goes to infinity of an. So we're told where to start, and given this, we can find the next value. We can always find the next value. So we're going to do this two ways. First, we're going to write down a bunch of terms. We're going to determine the value of an for a bunch of terms and look for a pattern, see where it's headed, and then I'll show you an alternate way of thinking about this as well. Okay, so that's what we want. So A1, A0 we're told is 7, so let's start there. A0 is 7. So A1 is going to be 1/4 times A0, which is 7, plus 6. And for this problem, it will be convenient to have a calculator that can deal with fractions and simplify them. So we want 1/4 times 7 plus 6. And you want to make sure that you have that as a fraction. And that's 31/4. Now, if you put this into your calculator correctly, we can start making these next values without very much work at all by saying that A2 is 1/4 of the previous answer, right? So this is AN, so that will be 31/4 plus 6. So I can just put in my calculator 1/4 times the answer that it just calculated, and then plus 6. So that's what I'm going to do. I'm going to do 1/4 multiplied by the answer. Remember that on the TI-8384, that second enter, that will bring up, or second answer, that's down by the decimal point, sorry, second answer down by the decimal point. So 1/4 times the answer plus 6, and then hit enter. Make sure you're converting it to the fractions, and so that is 127/16. 127/16. And the next one and so we'll find that we get 511/64. And if we keep going, I'll find that A4 is 2047/256. And A5 is 4095 divided by 1024. And we're going to start looking for a pattern just at this point. The denominators work out pretty nicely. This is 4, this is 16. Look what we're doing. We're multiplying by 4 each time to get to the next denominator. I'm going to think about that in a slightly different way. I'm going to write 7 as 7/1. And then I'm going to think about these as powers of 2. This is 2 to the 0. This is 2 squared. This is 2 to the 4th. This is 2 to the 6th. So the denominators here are even powers of 2. So this is 2 to the 2n. You could think about that as 4 to the n as well. It works out to be the same thing. But these are even powers of 2. 2, 0, 2 squared, 2, 4, 2, 6, and so on. The numerators are a little harder to see, but you should think about this as the 7, 31, 127. I'm looking as very similar to 8, 32, 128, which are also powers of 2. This is 2 cubed. This is 2 to the 5th. This is 2 to the 7th. So now it's odd powers of 2, but then we have to take 1 away from them. So we're seeing odd powers of 2 and then taking away 1. We just have to be careful that they are going to match up with what we've written down here. What was the very first n value? We decided that based on my denominator, I'm starting at n equals 0, because if I plug 0 in for n, I will get 2 to the 0, which is 1. So if I'm starting at n equals 0, I need to end up getting 3 as my first power of 2. That means that I'm going to need 2 to the 2n plus 3. Now that's always going to be odd because 2n is always going to be even. So this is always even plus 3, which will be an odd number, and will always get me to the next odd number. It's just like 2n plus 1, but the fact that I have a 3 in here just means that I'm jumping to the next odd one to start. Notice when I plug n equals 0 in, then that becomes 2 to the 3, which is the 8 that I need it to be, but then I'm subtracting 1. Okay, so now when I plug n equals 0 in, just to be clear, n equals 0 makes 2 to the 3 minus 1, that's 8 minus 1, which is 7, like I need it to be. And then the denominator is 2 to the 0, which is 1, like I need it to be. If I plug n equal 1 in, then I get 2 to the 5, which is 32. Minus 1 makes the 31 that we see. Plugging n equal 1 in down here makes 2 to the 4, which is the 4 that we need. And the rest of these will also all work out as necessary. So this is an explicit formula for an. We've just found an explicit formula for an by writing down the numbers and looking for a pattern. Okay, so now what? Now we're asked, what is the limit of this as n goes to infinity? So let me save this formula. I want the limit as n goes to infinity of 2 to the 2n plus 3 minus 1 over 2 to the 2n. Let's just do some algebra. That 2n plus 3, that's 2 to the 2n times 2 cubed minus 1 over 2n. 2 to the 2n. Right, that's how the exponents work. This is 2 to the n, this is 3. I can add them up to make 2n plus 3. So we're still looking at that limit. Now I'm going to divide this into both pieces to say limit as n goes to infinity of 2 to the n times 2 to the 3 over 2 to the 2n, 2 to the 2n up there, sorry, over 2 to the 2n minus 1 over 2 to the 2n. The limit as n goes to infinity. These cancel, and I'm left with limit as n goes to infinity of 2 cubed. What happens when n goes to infinity here? This goes to 0, minus 0. And so in the end I'm going to get 8 as my final limit. Now, let me show you an alternate way of thinking about that, which actually is easier. It's easier to do the calculations, maybe a bit harder to understand the idea. An alternate way of thinking about this is to take this an plus 1 as 1/4 an plus 6 and take the limit, let me leave some space here, what I want to do is take the limit as n goes to infinity of both sides. The idea here is that the limit of the n plus first terms is the same as the limit of the nth terms. This is just one ahead, it's always one step ahead, but when I take the limit, I'm just getting to the limit in the very end. So these things are exactly the same. So I can think about this as, so first let's just say this. I'm going to distribute this limit, which I'm allowed to do because this is just a sum. The limit of a sum is the sum of the limits. I can bring the 1/4 out. And the limit of 6 is just 6. And the point here, again, is that limit as n goes to infinity of an plus 1 is just the same as the limit as n goes to infinity of an. The limit is the same. So this thing is the same as this thing. So just to simplify my life a little bit, let me just call that x so I don't have to keep writing limit. So that's x is equal to 1/4 x plus 6. So if you want to skip all of this writing of the limit, really all that we did was we thought about an plus 1 as being the same as an, and the limit becomes x, and we have x is equal to 1/4 x plus 6. So if x is equal to 1/4 x plus 6, and we solve for x, we bring the 1/4 over, that becomes 3/4 x is equal to 6. So that x is equal to 6 times 4/3, which is 24/3, which is 8, which is exactly the same limit that we came up with by writing out a bunch of terms and looking for a pattern. And then doing some algebra. This is much easier in the end. But hopefully putting the two together convinces you that they're both reasonable ways to approach the problem.